So, we were looking at the problems in the charge pump PLL, which we have introduced just few sessions back. So, let us look at another problem in the charge pump, and another problem in the charge pump is associated with the uh, charge pump and loop filter action together. So, let me just redraw that charge pump plus loop filter. So, you have this ICP followed by the loop filter response. Okay. So, this is up and down, let us not worry about up and down now, ICP, and this is ICP going in the system. Now, what happens is, we have seen this multiple times, that let us say your up and down pulses, you have some kind of phase error. So, I am going to draw my up pulse like this. It is periodic in nature. Okay, you can think about it, and this is up, and down will also be a similar square pulse with a lesser width. Whether up is larger or down is larger, that depends on the phase error. Okay. So, in response to this up and down pulse, these up and down pulses, you have ICP, small ICP, the current which flows through the loop filter is shown here. Okay. Now, when this particular ICP current is pumped into the loop filter, earlier we drew the control voltage. This voltage is, by the way, control voltage. The control voltage happens to be like this, a jump, integration, and jump like this, and then comes back. Okay. If you think about it, what I am trying to do is, suddenly you can think that suddenly you have ICP current flowing through a resistor and capacitor, right. So, whatever value of the voltage, this particular voltage before this rising edge may not be equal to 0, this is, it will be some voltage, right. So, as soon as you start pumping the current ICP, the capacitor voltage cannot change instantaneously. So, what you see here is a jump in the voltage, and this jump is equal to ICP R. Okay. The jump here is ICP times R, and then that voltage, the current keeps on integrating over the capacitor, the voltage keeps on increasing linearly, right. So, if I call this as Vc, Vc is initially 0 and then it keeps on increasing. So, this Vc and Vr, just the voltage across the capacitor and resistor, can be drawn here. So, I will say that there is a voltage like this, okay. So, you have a voltage like this is VR, voltage across the resistor, and voltage across the capacitor is something like this. Voltage across the capacitor changes slowly, right, and V control is VR plus Vc. So, what is the problem with this? Well, the problem is that your control voltage, which is connected to the oscillator, is changing every reference frequency, and for multiple reasons. You have this oscillator here, this is your control voltage. So, the control voltage of the oscillator changes every reference frequency for multiple reasons, right, whether you have phase error, you have charge, there are some problems in the charge pump and other things. those things will happen. So, because of this change in the control voltage at the reference frequency, you modulate the frequency of the oscillator with VR, like pulse waveform. Okay. So, I will say VR modulates oscillator frequency every reference period, every reference clock period. Okay. This is my reference clock period. Now, well, the waveform which you are seeing is a more or less square waveform with the duty cycle, and this is whatever delta t error you are going to have in steady state. It depends, the pulse width depends on that. So, this VR can be written as, in terms of the Fourier series, n cosine of n omega r t plus Bn times sin omega r t, where omega r is equal to 2 pi by t, the reference frequency is your reference frequency in radians. Okay. So, if we are modulating, so now you can write Fourier series for this VR waveform. It is modulating your oscillator's frequency, and if you pick up even the first one, omega r, where n is equal to 1, then you see that you are modulating oscillator's voltage at omega r, which is finally leading to omega out plus minus omega r. These components will come. Okay. And the components at omega out plus omega r, they are normally termed as reference spurs. So, if you look at the spectrum of the oscillator in a given PLL, you will find that you have your omega out and you have other components also, and one of the dominant component is omega out plus omega r, another is omega out minus omega r. So, the problem of reference spur exists because there is an instant change in the control voltage of the oscillator. Okay. It is more prominent, and it is not only that you are going to have omega out plus minus omega r, you will also see, depending on your output frequency, you are going to see other higher harmonics also, plus minus 2 omega r and so on, right. So, now if we realize that this is the problem, right, because of this control voltage variation, which we also termed as control voltage ripple. Okay, it is a ripple at the control voltage. So, because of the control voltage ripple, we modulate the output frequency of the oscillator, and we have unwanted components in the form of reference spurs, right. We need to, if we know the problem, then it is really good, right, we can find a solution. So, now what we need to do is this: we cannot avoid the phase error information coming from the PFT plus charge from every reference frequency, that is not avoidable, right. So, what we need to do is the following. Let us say that I am going to get this current ICP coming from the charge pump in the loop filter, and if I have this loop filter, I know that what will happen is there will be a jump. So, if I do not want that this should have a jump, what I can do is I can provide another low impedance path to our ICP current, which is coming at every reference frequency. So, that low impedance path can be provided by a capacitor, okay, with value C2. So, for just hand waving analysis, let me put it that way, I have ICP, it sees two paths, one with C2 and another with RC1. If I make sure that the impedance provided by 1 over j omega C2 at omega r frequency or your reference frequency, right, that the impedance provided by 1 over by C2, which is going to be 1 over j omega r times C2. If this impedance is much smaller than the impedance provided by our R plus C1, then it will help in reducing the ripple on the control voltage. So, in order to do that, what do I need to do? I need to have R plus 1 over j omega r C1. I want to do this, right. If that is the case, you can just rewrite it, omega r times C2 is lesser than the magnitude of 1 plus j omega r C1 times r divided by omega r C1. It goes off. Okay. So, C2 has to be much larger than C1 divided by 1 plus j omega r C1 times r. Omega r refers to the reference frequency. Okay. So, if you look at it, I need to provide just from this. Earlier we have seen that we chose C1 and R such that we had in proper phase margin and other things. Now, I have to choose C2 which is larger than some particular component value, right, and depending on the C2 capacitor I can bypass the ripple voltage. Okay. So, this C2 is often termed as C2 is called as ripple bypass capacitor. Because we introduce it as a ripple suppression. Okay. Now, if we have C2 as a ripple bypass capacitor, this analysis is just a hand waving that okay, the impedance provided by 2, but the combined impedance here of RC1 plus C2 actually introduces another pole in the loop filter, okay, which increases the order of the PLL and it questions the stability of the PLL. Okay. So, now let us just redraw our PLL with the ripple bypass capacitor. So, this the charge pump, another set of switches controlling here, and then this goes through a loop filter using RC1 and then C2 RC1 which goes to the VCO. So, what you see here is that when we try to solve the problem, if we create another problem, then that is we have to check it that how much problem we solved and how much problem we created. So, here we have the reference voltage, this is our out, this comes ICP and this is the control voltage. Okay. The small signal model of this PLL is again a simple one that you have the phase error, right, multiplied by, I will write it as ICP by 2 pi going into the loop filter with C1 and C2 which gets multiplied by KVCO over S. Okay. This is plus, this is minus, this is ICP, this is V control of S. Okay. So, phi ref and phi out. Look at Now, the loop gain. Okay. So, loop gain for this particular PLL is ICP by 2 pi into R plus 1 over SC1 in parallel with 1 over SC2. If you write it together, you will find this is 1 over RC1 divided by 1 plus SR C1 C2 divided by C1 plus C2 into 1 over or KVCO S square C1 plus C2. Okay. So, now with this new loop gain, we will see whether this loop is stable or not. Okay. So, here you have two poles first at omega p1 and omega p2 equal to 0. You have third pole at 1 over R C1 C2 by C1 plus C2. Okay. By the way, you must be used to writing this poles, whether it is a left half plane pole or right half plane pole. Here when I am writing omega p3 is I am saying it as a pole, but just the frequency part omega p3. Poles S1 is 0, S2 is 0 and S3 is minus omega p3. Okay. So, I want to avoid any confusion here. The omega p3 is 1 by R C1 C2 by C1 plus C2, not our pole. Now, 0 in Laplace domain is actually at minus 1 over R C1, and the 0 frequency which I use in the expression is omega z, which I write as 1 over R C1. So, the loop gain expression can be rewritten as ICP KVCO divided by 2 pi S square C1 plus C2 into 1 plus S pi omega z divided by 1 plus S pi omega P3. Okay. The angle of this loop gain at any given frequency is equal to minus 180 degree plus tan inverse of omega by omega z minus tan inverse of omega by omega P3. Okay. So, let us look whether our system is stable or not. First, I am going to plot the loop gain with respect to omega. So, this is magnitude of loop gain in dB, right. What you see is that you are having two poles at 0. So, you will have minus 40 dB per decade, then you have a 0. So, it will be like this. Then depending on the position of our omega p3, I am going to have the second pole. This is one option which you see, that my omega p3 is coming after omega u. Okay. Looking at these things, you can very well say omega p3 is surely going to be larger than omega z, because C1 C2 by C1 plus C2 is lesser than C1. But whether omega p3 is going to be greater than omega u or less than omega du, that we do not know. Okay. So, if we have such kind of loop gain, then the phase plot, corresponding phase plot is going to be like this. So, at omega u, you will have so, I will just take another line here. Okay. So, this is minus 180, minus 135, minus 90, minus 45 degree, right. So, it starts with the minus 180 degree, it has a 0. So, it goes to minus 135, If omega p3 comes much later, then it may reach close to minus 90, and when comes omega p3, it may again go to minus 135. And then finally, what you see here is that omega p3 is a pole. So, at maximum this can introduce 90 degree, this can introduce 90 degree, which cancels out. So, as frequency tends to infinity, you may go to 0. Okay. So, here the phase margin which you may calculate appears to be this. Now, in place of the omega p3 location which we have seen, if it happens that omega p3 comes here, because you increase C2, so omega p3 can change its location. If omega p3 comes here, right, then what you see is that you will surely have minus 135 degree, and then you have another pole. So, before it reaches, what you can say is your frequency comes, it does not reach minus 135, does not reach minus 90 degree. So, what you may see is the frequency is, the phase is actually much lesser, right. It is not going to be minus 135, it will be slightly larger than maybe minus 135, and then it will finally go like this. So, these are the two cases which I have seen, and if you now you want to calculate the phase margin, it is going to be only this much. Okay. So, this I will write this as omega p3 dash. So, omega p3 dash is lesser than omega p3, and you can say C2 dash is greater than C2. C2 dash is the capacitor which you are using for omega p3 dash, and it appears that the phase margin is reduced, right. So, now as we introduced another pole in the system, what we found is that yes, you can reduce the control voltage ripple, but you make your PLL more susceptible to instability. Well, we will not have a PLL which is unstable. So, we will try to make it stable with desired phase margin. But if you do not pay attention, if you just use C2 with a very large value, then what you will see, your phase margin is going as phase margin is not there, 0 and pole cancel out, right, and with no phase margin you will have unstable PLL. So, we need to look at that how we are going to choose this phase margin, how we place omega p3 in our system. Okay. Thank you.